would state that we must build a device that is capable of moving up to 4 meters to a wall that can accelerate from the target, decelerate at the wall, and do the reverse to get back to the initial position. The vehicle must return to the same point it left from using a mechanical measurement device. The wheels must be aligned so that the vehicle does not veer off track on the way to or from the wall. All this must be done well inside 2 minutes, and this should have a cost no greater than 30 pounds. Our objectives are: our vehicle wouldn't have a mass bigger than 3 kilograms, which will account for much less friction. We should have a maximum distance of 10 millimeters with the target. The vehicle should have a minimum peak velocity of 0.2 meters per second. The vehicle will be able to overcome the static friction on wood. The vehicle will be able to make 3 runs ranging from short range, mid range to long range, therefore will be relatively durable. Our assumptions moving forward with the calculations are: all drag forces that are non-related to friction will be assumed to have a negligible effect on the calculations of the vehicle. The dynamic peak friction coefficient and the static peak coefficient of wood will be taken as similar, and it will have a value of 0.7. Other than the springs, all objects will be taken as rigid bodies, and rolling resistance is negligible as the small rubber-coated wheels and the wooden track will bail.
Drive, distance measuring and control systems. A 6-volt motor connected to the wheels with gear ratio 80 between them will propel the vehicle. For measurement, a belt and 2 pulleys with a stopper attached to the belt. The stopper will initially be in contact with the vehicle body, and when the vehicle moves away from the target, the stopper will move a distance proportional to the vehicle. Once the vehicle reverses, it will move until the stopper hits the vehicle body again, and a switch will turn off the power. For the reverse system, a simple circuit will use a button and a switch on the bumper, which is attached to the vehicle with 2 springs. The button will turn off the power while the bumper is in contact with the wall, and the switch will reverse to the direction of the current through the motor. The power needs to be switched off while the springs are in compression to prevent the motor causing the vehicle to lose traction, which would affect the accuracy of the measurement system and misalign the wheels. Once the springs have pushed the vehicle away from the wall, no longer in contact, the power will return to the motor with opposite polarity so that the vehicle reverses back to the target, where the stopper will press another button to turn off the power.
Moving on to our CAD model, we try to make a design that is lightweight but also has every characteristic and component we needed to succeed in the IMEKey design challenge. The overall dimensions of our repeatable vehicle are 375 millimeters in length, 300 millimeters in width, and 40 millimeters in height, so it is within the range that the rules state. We use different materials to reach our goal of low weight, low cost, and maximum performance. So we use metal for our axles, plastic for the gears and the wheels, rubber for the tires, and oak for our main body and the bumper. In addition to this, we use multiple gears to get the desired gear ratio of 1:80 we needed in order to move the car forwards and backwards. And we use a timing belt and 2 pulleys to measure the distance covered mechanically.
To make sure our model was realistic, we did some ballpark calculations. We thought our vehicle should cover a distance of 8 meters in 30 to 60 seconds. This gave an average speed of 0.13 to 0.27 meters per second. We attempted to find the max speed using the information about the motor provided by the manufacturer, as well as using first principles. This gave us a max speed of 0.271 meters per second, which was in line with what we estimated, so that reassured us with our model. Next, we used Newton's second law and the conservation of energy to find the maximum deceleration at the wall. Since our motor should be switched off before the springs in the end are compressed, we have a simple equation equating kinetic energy to elastic potential energy. Using this method, we found the deceleration to be 4.458 meters per second squared.